Well, I apologize for the quiz problem. Normally at this point I would ask about questions for the quiz, but since half of you haven't taken it, we probably don't want to talk about questions, so we can handle those later. But I would like to start off with, not a problem. We've been working on the 9-digit Social Security number. As of last Friday when we left class, we had discovered a couple of things about that number. One, that the 5th digit or middle digit was a 5. And the reason we said that was a 5 was because the number ending, the 5-digit number ending there, to be divisible by 5 has to end in either a 0 or a 5, and there's no 0 in this one, so it has to be a 5. Question?
I found out that that doesn't have to be that way.
Oh, really?
Let me see if I can find a note.
So it could be something other than a 5.
At least I don't know if it would completely.
So have you got something else it could be? Sure. You want to put it over on a sideboard there?
I'm just not sure. I've got a couple of them that I did. And I only got, and it's not to say that it would have to be, because this problem only gets to 5, the way that I found it, but you can have a number divisible by 5 without having it be the number 5, right?
Go ahead and fill your number in that you think will.
9, 7, so then you get 16, which is divisible by 2. And then 6, 22, not 22. It was kind of
Let me see if, let me ask you, Devin, ask you some questions to see if we understand the problem in the same way. You think that the first 2 digits are divisible by 2? The number formed by the first 2 digits divisible by 2?
So 9 plus 7 is 16.
Okay, that's what I thought you were thinking.
Is that not?
Okay, so it has nothing to do with the sum of these. It's the number formed by the first 2 digits is divisible by 2. So 97 is not divisible by 2, so that's not it. That's fine. That's fine. Just make a shift. So 976 would have to be divisible by 3. The number 976, not the sum of the digits. That number. So I'm guessing there might even be some here who were interpreting that way.
Yeah.
So that helps us. But I want 9's got to be divisible by 1. 97's got to be divisible by 2. 976, that number, the 976, has to be divisible by 3. Not their sums. Okay? All right? If we don't understand the problem the same way, we won't pursue it in the same way, and our results will be different. Not that hers aren't going to be accurate for her interpretation, it's just that that's not what we intend. Does that make sense? Okay. Thank you for that. What other discoveries did we have on Friday? Yes.
That they're gonna go odd, even, all the way across.
Because in order for a number that's divisible by 2, it has to be an even number. And to be an even number, the ones place, the units place, has to be even, right? And same with, if you're going to be divisible by 4, the ones place, the units place has got to be even, correct? So it goes odd, even, odd, even, all the way across. Did anybody make any discoveries beyond those 2 that we had on Friday? I don't want anybody sharing any numbers. If you think you found the number or the numbers that work, I don't want those. I just want discoveries about the number.
What
Go ahead.
if you discovered numbers that don't work?
Oh, that's helpful too. That's helpful also, yeah. Did you want to give us one?
It's just a quick thing, but when I was going through all the numbers trying to figure out what it was, I noticed that the 4th number was always a 6 and the 6th one was always a 4.
You mean on the ones you tried?
Yeah. And they worked up to the 6th number, if that makes any sense.
Okay, does that make them accurate, or is there some particular reason why they have to be that?
I don't know, they don't necessarily have to be that, I just noticed a lot of them were that way, and I'm
Okay.
not sure why.
Okay. Anybody else have a discovery that they, yes?
So between all the numbers, there's a difference of 3, so like 1 and 4, there's a difference of 3, 4 and 7, there's a difference of 3. But if it's 2 and 7, there's a difference of 9, which is oddly the median number.
You mean you're either going up 3 or down 3?
And then when you get closer to the median, it becomes a difference of 5. So it's 8 and 3, 7 and 3, 5.
Okay. Okay, so you think you have found a number that works?
So numbers that are divisible by 3, 6, and 9, the digits of those numbers have to add up to something that is divisible, or has to add up to something that's divisible by 3.
Is that true? Say that again, please.
Okay, so numbers that are divisible by 3, 6, and 9. So this applies to the number that you want to put in the 3rd spot, 6th spot, and the 9th spot, primarily. Like those are the numbers we're looking at. The digits of those numbers have to add up to something that's divisible by 3. So like if you added up the first 3 digits, if they don't add up to something that's divisible by 3, then you know that that's not correct.
Okay. Why does that work?
Why is that a rule about those numbers?
Yeah. Where did you get that from, in other words?
I don't know. That's something I have always known. I don't
You
know
were
why.
born knowing it,
I
right?
was, yes, I came out of the womb knowing that. I actually, yeah, I have no idea why.
She can't remember when she learned it. Aren't there a lot of things like that? How many of you have heard that? That if a number is divisible by 3, no matter what its length is, if you were to add all the digits up, the sum is divisible by 3. Which may be why Devin was getting those kinds of ideas for what she was doing there, adding the digits up. Okay? So that could help us to solve this thing, perhaps. Okay? Anybody else have a...
Well, going off of that, then you know, like, you know certain numbers that the first one can and cannot be. Because it had, oh no, that was dumb of me to say.
Why? What?
Well, I always thought the first one had to be a 1, but then I figured out a number where it wasn't a 1.
Okay.
I don't know, never mind, that was weird though.
I'm not too sure it was. I just think maybe we need to say it in a way that...
Yeah, maybe I should get my words right.
Anybody else want to... Well, let's keep thinking about this number. And what I'd like you to do, let's switch gears a bit and talk about a part of the homework. I'd like you to turn to someone next to you and tell them if someone hands you a whole number, how you can look at it and that fast tell whether or not it has an odd number of factors or an even number of factors. Would you do that? Okay. How do you tell whether a number is going to have an odd number of factors or an even number of factors? And then tell them how you know, why that's the case. Okay?
Okay, I was like, I remember that. It's
Okay, I need someone who came to class today not knowing how to tell whether it had an odd number of factors or an even number of factors, but because of your discussion you just had, you can now answer that. Yes? Anybody in that category? Go.
My brain just completely dropped when I was thinking about that. So, but my partner was telling me how like all like the squares, like 9 and 16 and 36, they're all going to have an odd number of factors just because you're going to have a set of factors that are going to be the same number, so you're going to have an odd number of factors for every square.
How many of you followed what she said? How many of you would like to ask her a question? Everyone's clear? Wow. See what great teaching you did? What you did to her so that she could do it. This is how it works, right? If you can explain something to someone so that it's clear, you've got it, right? All right. What else did we learn out of that activity? Anybody? Well, I want to share with you, how many of you have graphing calculators here? Okay. Let me show you the way to find all the factors of a number. I'm going to let you kind of make sure I'm in the view. If not, twist or turn or whatever. I'm going to show you how to find all the factors of a number if you own a graphing calculator. Let's say we want to know all the factors of 60. Okay? I was taught this trick by an 8th grader. I'm not kidding you. I mean, it made sense to me, but I'd never seen it before, and I thought, wow, that's cool. So what you do is, you got your calculator up, you hit the y equals button, you go to y equals, and if you've got any equations in there, clear them out. If you don't have any, just type this in, 60 divided by x, and your x button is the button that has the xt theta on it, right near the top there. Okay? Now let's stop and think what this does. This says take 60 and divide it by x and give the result. Okay, and then the student says, now go to the table, which is second graph for most of your calculators, if you've got a TI-83 or 84. And it will show you what your x is and your y. So most of them are set to start at 1. When 1 is divided into 60, it goes in 60 times. And when 2 goes in, it goes in 30 times. And when 3, it's 20. And the student said, you just look down the y column and anything that has a whole number in it is a factor of 60 and its partner is over here. And if it doesn't have a, so when would be the, let's do the next, 4 would be what? 15, and 5 would be 12, and 6 would be what? 10, and 7 would be what? Not a whole number, right? And 8? Not a, and when would he stop? When did this student stop? That's what I asked him. I said, so how do you know you've got them all? I could go down so that my x got clear to what? 60, and its partner would be 1, right? Do I have to go clear down to 60? No? How far do I have to go? To what?
Till they start repeating.
Till they start repeating. What do you mean?
Like the x is 10 and the y is 6.
Oh, by the time we get to the x being 10 and the y 6, that's, we would stop because we already got 6 and 10. So guess what? 7 didn't work, 8 didn't work, neither does 9, and 10 is a repeat of this. So guess what? There's all the factors of 60. That's pretty cool, isn't it? Pretty cool way to find them if you've got the technology. What would happen if I put 36? Y equals 36 divided by x. We would have what? 1 and 36, 2 and 18, 3 and 12, 4 and 9. I'd try a 5, but I'd get what? 7 point something, right? Because, and then what? 6 with a 6. And you'll notice that I've got 2, 4, 6, 8. This is not, right? And 9. Because I don't count both of these, because you don't say, well, it has a factor of 6 and a factor of 6. That's being redundant. And I move that we stamp out and abolish redundancy. Somebody caught it. So we have an odd number, whereas over here we have an even number, right? Why is it even? Because it's not a perfect square. And only the perfect squares have a number that is its very own partner that we don't count twice, and therefore it's because every factor has a partner, right? It's just that this partner is itself. Is that clear for everybody? Okay. Did you get the vocabulary that goes with these? If it's got exactly 2, it's what? Prime. Number. Let me warn you about something that you might see on a test, or you might just be thinking about. Let's get a definition for prime. Well, let's define prime, and then we'll decide if one's prime or not, okay? Would someone like to give a definition for prime?
Well, in elementary school, we always said a prime number has, the factors are 1 in itself.
Okay.
That's,
if we define prime numbers to be a number who has a factor of 1 in itself, is 1 a prime number? Yes, because it's got a factor of 1 and itself is 1. Right? That is not a good definition for a prime. But I'm sure glad you brought it up because that's what everybody memorizes. And it's almost right. Because it tells us what all the prime numbers are except it classifies 1 as a prime and 1 is not a prime. Why not? Who has another definition maybe that would be more accurate? Yeah.
A number that has only 2 factors.
Could I change one word? A number that has exactly 2 factors. Now does 1 work? Because it has 1, right? In fact, it's the only whole number that has 1. Everything else has 2 or more, right? But if it has exactly 2, and in that case, just what you said, it is 1 and itself. But if we define prime numbers with that definition, we end up with saying 1 is a prime number and it's not. Okay? Because it doesn't have exactly 2 factors. It only has 1. Okay. So if they're not 1 and they're not prime, what are they? What's the other one?
Composite.
Composite. And composite numbers are what then? What would you define? How would you define those?
A number that has more than 2 factors.
Has more than 2 factors. We okay? Yes, question.
Are we deciding that 1 is a prime number?
1 is, does it fit our definition?
No.
Then it's not. That's how you decide something. Does it fit the definition? If it does, it is one of those. We could define a lion. And then you would just say, does this animal fit the definition? If it does, it's a lion. I mean, and if we have an adequate definition for lion, then it should work for any animal.
So in our number theory glossary, are we just including the definition, or what exactly are you expecting when we turn in all the definitions?
I'd like it in your own words. This one probably would be best if we had it. In fact, you might write by prime, do not use the definition of what? 1 in itself, because that would mean 1 is prime and 1's not. You might put that just underneath there. Just a little.
So definition and just anything else you want
Yeah,
to include, but
sure.
not like draw a picture or anything.
You know, if a picture works for sometimes a picture is really good, but I don't know how a picture would help with primes.
Okay, thank you.
All right?
So does 1 have a name then? Or is it just 1? If it's
1's
not
kind of a
prime, it's not
unique
composite,
number. It's a non-prime, non-composite number. We call it the unit, and it's very unique in that aspect. Okay? All right. Everybody got a definition for composite? Most of you have learned how to do this, but we're going to review it. Prime factorization. This becomes extremely important for us in this unit and for understanding a whole bunch of things. To find the prime factorization of a number, here's what we do. Let's just take 60. I'm going to show you 2 methods. I'll show you my favorite method first, and then I'll show you my next favorite method, but I like the tree method best. And the reason I like the tree method is it provides me with a lot of flexibility. Since I grew up, when I was in 1st and 2nd grade, we had over 1,000 laying hens, and I learned my dozens real easily. And I know that 5 dozen is 60. I don't know if you know. I was born with that, okay? It seems like it, because from doing eggs, I just learned the dozens. So I can say a dozen times 5 is this. And then I ask, are these 2 numbers prime? This one is, so I'll underline it. This one's not, so I'll break it down some more. And here I have another choice. I can be thinking 3 times 4, or I can be thinking 2 times 6. And does it matter? No, not with this method. So I'll put 6 and 2. 2 is now prime, but 6 isn't, so I keep going. If it's prime, you underline it. If not, you just keep breaking it down. 2, the only way I can think of is 2 and 3, right? And now they're both prime. So now, the numbers that are underlined, I have 2 times 3 times 2 times 5. We call this the prime factorization. Sometimes we like to write them with shortcuts because mathematicians like to write less and express things. And so we'll do what we call a prime power factorization, and I'll say, I notice this 2 occurs as a factor twice, so I'll write it 2 squared times 3 times 5. And I could put a 1 on the 3 and the 5, but everyone knows that if you don't write the exponent, it is understood to be 1, correct? This is the prime power factorization. This is the prime factorization. And the interesting thing about, in fact, it is called the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that every number has a unique prime power factorization. If you don't consider the commutative property, this right here is also the same as 3 times 2 squared times 5. Does everybody see that? All I'm doing is commuting. If you don't consider the commutative property, it is unique. In other words, if you were to write it, typically we'll write it with the smallest prime, then the next smallest, and so on, and that is always unique, no matter how you do it. Even if you didn't know that there were 5 dozen, you could start out with 6 times 10, right? And 6 would break out down into 2 times 3, and 10 into 2 times 5. And guess what I've got? 2 squared times 3 times 5. It doesn't matter. Some of you would say, oh, when I see 60, I don't go 6 and 10, I go 30 and 2. That one's prime. Keep breaking it down. 15 and 2. Oops. 3 and 5, and now I have what? 2 squared times 3 times 5. It doesn't matter how you do it, you always arrive at the, because 60 has a unique prime power factorization. This is it. No other number has it. That's the fundamental theorem of arithmetic. So the tree method, it provides lots of flexibility. We did 3 of several ways we could have done that. Let me show you the other method that we need to be aware of, and that is the division method. So I start with 60, and then for some reason we just go down like this and put our, so the requirement on the division method, and the reason why I don't like it quite as well, is you must start with a prime number. I couldn't choose a 12 and put it out here and say it went in 5 times. I have to start with the prime numbers. I'm going to start with 2. Goes in 30 times. Is this one prime? No. Then I start with another prime. It doesn't matter which prime. I can see it's still even, so I could take another 2, but I could put a 3 there as well, because I know 3. Let's just do a 2. Then that goes in 15 times. 15 now, is it prime? No. No. So I pick another prime and 3 and 5, and when I finally get a prime number down here, I know I'm done. If I've got primes out here all the way, and notice I've got 2 times 2 times 3 times 5. Same thing. Question, comment?
When you're picking prime numbers, are you picking them to make sure that they go into it evenly?
Yes. There's got to be divisors of the number you're talking about. And so the number of times it goes in has to be a whole number. Okay? Good question. Yes?
So the fundamental theorem of arithmetic only works with 60?
Oh, no.
Oh, it works.
Give me a number. Any number.
14.
14.
2 and 7.
2 and 7. 2 prime?
Yep.
Yes. 7 prime?
Yep.
Yes. So it's 2 times 7. The only number that has the prime power factorization of 2 times 7 is 14. So every number you would give me would have a unique one. No one would have the same prime power factorization. That's what the fundamental theorem of arithmetic says. Yes?
So that's how you would define it. No other number has the same prime factorization as...
Every whole number has a unique
Okay.
prime power factorization, except for 1, of course, right? because one is really unique, is if I go like this, that's not prime, right? It's the only factor I can get out of it, right? And then, do I say, is it 1 to the first, or is it 1 to the fifth? Anyway, it's not prime, so every number greater than 1 has a unique prime power factorization. We okay? Questions? Everybody? This has a little bit of flexibility. I could have gone 60 and started with a 3 at first and got 20. And then I could have said 5 goes into there 4 times, and then 2 goes into there twice. Now but I end up with the same. But the requirement is you have to have primes out here, and then when you get to the last prime, you stop.
Can we do another example without 60?
Sure.
Could you do one like 47?
Since every number works, you can give me anything. Go ahead.
So like 47?
47, go.
It's a prime, isn't it?
What is its prime power factorization?
1 and 4.
Don't put 1 because 1's not a prime. Don't ever put 1 in here. It's just 47 to the first. In fact, every prime number is just itself once, right? That makes sense?
Kind of, yeah. Okay, so then what if you did one like 50?
50. So everybody try it. Go. When you're done, look at your neighbor's prime power factorization. It better be the same as yours, unless you just, have a different order. But check with a neighbor. Did you both get 2 times 5 squared? Okay. What about 243? Is it prime? If it is, its prime power factorization is 243 to the first and we're done, right? It's not? How do you know?
The method we discussed earlier, you add the 3 numbers and it's
Oh.
divisible by 3.
Yeah, let's use this little trick. 2 plus 4 plus 3 is
9.
9. So that means what?
It's divisible by 3.
It's divisible by 3, and we'll learn that it's also divisible by 9. But so I'm going to put this 3 out here. 3 goes into 24, 81 times. Is that one prime? No? What?
9.
You can't put a non-prime out
Oh,
here.
yeah. 3.
3 goes in there. 27.
3.
3 goes in there 9 times. 3 goes in there 3 times. Guess what? It's 3 to the 5th is the prime power factorization. No other number has that besides 243. It's unique.
Is this called prime factorization or prime power factorization?
This is called prime factorization. When you put it with the powers, that's when we call it prime power factorization. This one here could be considered prime factorization,
Yeah.
but there's no powers there.
Yeah.
And we frequently, and later on, those powers are going to become very important for us.
Yeah.
Okay, good question. You guys are asking great questions today. Anybody have a question about either of the our 2 methods for finding prime factorization? We're okay there? Anybody have any other questions that came out of the homework? We've already discussed the odd even, right? We've discussed the ones that have exactly 2, the ones that have more than 2. Did anybody get anything else out of there, or have any questions you want to ask about the?
There was a question on the homework where it asked how many ways can you find the prime number, like in the example. We had to find the factors of 255. Instead of doing 2 times 7 times 7 times 2, I did just 51 times 5.
What was it?
I don't remember. It was on the, I saw it on the key, but I didn't write it down.
So what was that number you just used?
255.
255. And you said what?
I just did 51 times 5. But in the home.
So here we go. 5 goes into there what?
51 times.
51. 5 goes into 25, 5, and 5 into 5. 51. So are we done? Is it 5 times 51?
No.
No.
51 is a prime.
How do you know?
Because it's divisible by 17.
And
Did
3.
you, were you born with that?
No, no,
What we just learned, if you add the two digits, 5 plus 1 is
6.
6. 6 is divisible by 3, so 51 is divisible by 3, right? So let's do it. 3 goes into their ones with a remainder of 2, 21, 17, 5 and 3, and is this prime? So what's the prime factorization?
3 times 5 times
3 times
17.
5 times 17. And if you want to do the prime power factorization, you could put 1s on there if you want. But, okay. Does that answer your question?
Yeah.
So 51 at first, when we look at it, looks like it might be prime. But you can see it's not, so. Okay. Anybody else? Yes.
I just think that it's wonderful when you're teaching factors to know how to teach both of them. Because I know for me, when I was learning about factors, the factor tree didn't make any sense to me. But being able to go back to division, which I learned way early on in math, like being able to divide it, helped me a lot more than the factor tree actually did. So,
Thank you.
yeah.
Thank you. And if anybody comes up with any other methods, just share with us how you learned how to do something. I think knowing more than one approach gives you that opportunity as a teacher to be able to say, here's what you might try if what I showed you doesn't work. Okay? Or better yet, have your student invent their own method for doing something and share it with the class.
So the point of this is just to find the factors that go into each number, right?
Yeah. Why would you want to know the prime power factorization of a number? Any ideas?
Did she just ask if this helps us find factors of the number? Was that your question?
I'm wondering why we'd be teaching this. Like, what is the significant role for it, kind of thing.
Okay. There's a whole bunch of reasons, including adding fractions, reducing fractions to their simplest form. All ties back to this, and before we're done with this unit, you'll see those. Let me just take a problem here and show you. Let me shine it over this way. I'll just kind of. Let's take a number that we don't even know what it is. You ready? Let's go a 5 here and a 7. I don't even know what that number is. Right now I don't. But guess what? I can tell you about that number. I can tell you that you could get it by going 20 times, I'm stretching myself out here just a bit. Let's try this one.
If it's 20 times.
Let's go 40 times 63 will give me that number. How do I know that? Let me just show you what I was doing in my head here. I took the 2 to the third, and that's what?
8.
8. And 8 times 5 is 40. What's left over after I've used all the 2's and the 5?
7 and
the 2 powers of 3, which is 9 and 7 is 63. So I don't know what the number is, but 40 times 63 will give it to me. Let me show you what else we could do. We could say 5 times 7 is 35, and its partner will be all of the other factors, which is what? 9 times 8, which is 72. So I don't know what the number is, but I know that 72 times 35 will give it to me. Are you with me? Let's try this one. 21 is a factor of this number. Everybody see how I know that? How do I know that? Because 7 and 3 are, and 7 times 3 make up 21. Now what's left over after I've taken the 7 and one of the 3's? The other 3, right? The 8, 3 times 8 is 24 times 5 is, that's not too hard. 20 times 5 is 100. 4 times 5 is 20, so 120. So 21 times 120 will give me the number. And I don't even know what the number is. Somebody else tell me a pair they could get out of here, and we don't even know what the number is. Go ahead. I've given you some examples. Yeah.
45.
45. And what's its partner going to be?
56.
56. How did you do it?
Well, I multiplied the 5 times the 3 squared.
Which is 9. 9 times 5 is?
45.
And what's left over?
The 8
The 8 times the 7. Did you see how she got it? We don't even know what this number is, but 56 times 45 will give it to us. Somebody do it again. Something different. Yes,
Well, you can do 35.
I've got that.
Oh, just kidding.
Okay, you're on the right track.
You do 36 times 70.
36. How did you get 36?
If you do 2 times 2, it's
2 of the 2's gives us 4 with
the 3 squared, which is
the 9, right? The 2 3's gives us 36. What's left over? 2.
2 times 5 times
2 times 5 is 10 times, so it's 70. We don't know what the number is, but 70 times 36 will give it to us. Good. Who else can do one?
You can do 10 times 252.
Ooh, how did you get that 252? Did you
well,
use your calculator, or was this all
I
your
was
brain?
doing it
Oh,
all
by
the
hand.
time. Yeah.
So the 10 came from?
From 5 times 2.
This 5 times one of the 2's.
Mm-hmm. And then you take the 2 squared times
Which
3
is
squared.
4 times 9 is 36.
And then you times that by 7.
36 times 7. You can do that in your head. 30 times 7 is 210, right? And 7 times 6 is 42. 42 and 210 is, that's not too good. All right. Anybody got another one for me? Yes.
30.
30. We haven't done that one yet. Where'd you get the 30 from?
2 times 3 times 5.
One of the 2's, one of the 3's, and the 5 gives us the 30. And what did you get your other number?
So there's 2 2's left, which is 4 times 3 times 7.
So there's 2 2's left. Times what?
Times 3.
Is 12.
12 times 7.
Is
84.
84. Anybody else?
I got 28
28
and 90.
and 90. Is she right? Where's the 28 going to come from?